Give our mic a second here. There we go. Yes. All right. We are live out at the fuel cell. Oh, don't worry, Steve. You're going to be in there. We got our friend Tom here. Steve, you can't see me. I'm on the phone right now. We got Professor Horvath. We are out at the fuel cells, so we're going to take a look at these. Tom, you want to get us started? What are we looking at here, Tom?
I always feel like I need to pull my mask down to talk.
They hear you okay if it's up. Either way, you're 6 feet away outside, so you're fine.
So here we got two fuel cells. There's natural gas comes into them. They burn natural gas, and then by way of some cathodes and anodes and a lot of other PFM.
I think you're going to have to tell them what PFM is. They don't know that term.
PFM is pure freaking magic. Anything past my understanding, we kind of just chalk it up as magic.
It's magic.
So fuel
PFM.
cells have a lot of that. There's a lot of proprietary information that goes in, and after you graduate and figure out what you're going to do, maybe you could learn. But right now, natural gas goes into them, electricity comes out, and heat comes out. Electricity flows through the electrical cabinet and then off through a gas switch.
The gas switch is inside the tent?
And the gas switch is when they make contact, there's an inert gas inside there so that the spark doesn't
cause any problems.
Yep. So
where are we on campus, by the way, to give people an idea?
We are right near Thornton Hospital, Retina Glaucoma Center, the Shiley Eye Center, on the other side of the highway.
The eye center would be what, like behind that building right there?
Yes, exactly. Yeah. So this is the East Campus. That's a chiller plant. These are the cooling towers for the chiller plant, just like my original home back over at the central plant. We operate this plant by way of computers. It's a satellite plant, we call it. So we operate the chillers and the cooling towers and the fuel cell. The fuel cell we really don't have to do anything to because it's always running and always making electricity.
So it's actually on now, right?
Yes.
Even though it's so quiet out here, it's on and running. It's not like the jet engines over at the central utilities plant.
Good observation, yes. 1.4 megawatts, 1.4 megawatts, so 2.8 megawatts.
That's science.
And the heat that comes off of it, this is the interesting part that I know a little bit about. The heat that comes off of it is somewhere between 700 and 800 degrees. And then that heat in the form of just gas, hot gas goes into an absorption chiller, a lithium bromide absorption chiller, and that heat boils the refrigerant, and then the refrigerant is able to make the cold water, and it's actually chill water that we make for the system. Now the whole campus over here is using about 3,000 gallons a minute. The exhaust from the fuel cell running through the absorber is only 450 gallons, so it's a small fraction of what's really needed.
Right.
But it's the fact that we're getting two bangs for the buck, if you will.
Right.
We're using natural gas, but we're producing electricity, and we are boiling lithium bromide to make chill water.
Because it's got to go somewhere, right? It's coming out at 700 degrees. You got to do something with it.
And by the time we take the heat away from it, we take about 400 degrees away from it to do our process. So that's free energy as far as we're concerned. Yeah. And the university and the research industry is all about trying to get more bang for your buck.
So at the end of the day, it's coming out up here, right? Those are our stacks that it's coming out of?
That's the stack, 350 degrees coming out of the top.
But that's after it's already gone through a chiller.
Right. You want to walk down this way?
Yeah, let's take a look.
So the byproduct is heat and water. So it takes water to run it.
So now this is the actual cell here, right?
Yes, that's where the electricity is produced, and the exhaust comes out.
So this is our 700-800 degree exhaust coming out?
Yes, sir.
Wow. That is some hot stuff.
And then the absorption chiller, the chiller is inside this cabinet. We can go take a peek inside there.
Okay. So this is, sorry, the second cell, right, over here?
Yes.
So we've got, what'd you say, it was 2.4 and 2.4, or 1.2
and 1.2? 1.4 and 1.4.
1.4 and 1.4, gotcha.
So yeah, megawatt and a half.
Yeah, I mean, it's just amazing. You can get right up next to the thing and you don't hear anything.
Yeah.
It's dead silent sitting over here. I mean, you hear a little bit of gas flowing around here and there, but I guess all the noise is actually coming from all the support equipment outside of the cell.
Yep, the blowers and the...
Huh.
So the actual chiller is...
Yeah, let's take a look in there.
I mean, look what they did to it. It's a chiller... But this is making 400 gallons a minute, 450 gallons a minute of 43 degree water.
Talk about clearance. That thing's really packed in there.
Yeah, it's taken apart when it needs to be serviced.
Jeez.
We'll come back.
They just like disassemble the outside building?
Yep, it comes apart.
Wow. Why bother with a building that size if it's so close to the same size of the equipment just to keep it housed from the elements? Yeah.
Not too concerned about the end user. So want to go look at the chiller plant?
Yeah, let's go inside there.
Come on.
So this is our other cell that we've got over here.
Electricity coming out.
High voltage.
An old cooling tower gearbox. The electric motor spins it, and then the fan, it's probably a 7-to-1 ratio.
That's what we were playing with on top of the tower last time, right? We could
Yes.
actually,
Yep,
you
these
were
were
able
the
to put your
blades
foot
of
on
that.
it. Yeah. I guess that's what they're working on right now. So normally I would suggest we hop up there and get inside, but we're not going to. But you can actually see right here. So they've got this tower off, and we just saw them pulling out of there, what, 10 minutes ago, something like that.
Old media.
Pulling out old media, so we'll take a look at some of that too when we get inside the chiller. So now what's the building that we're going to go into here?
This is called the East Campus Chiller Plant, ECCP. And it's my understanding that the tiles on the side of the building are very special. They came from far away. They were very expensive. But yeah, a lot of money was put into the aesthetics of the building. And
yeah. Now, given that you're over at the Central Utilities plant and recognizing that your boss Tim probably will never see this, does that make you angry that they got the nicer looking building than you did?
That they have the what?
That they have the nicer looking building than you do?
No, not at all.
No, not at all. No,
Not
sir.
at all.
Okay. There's no resentment there at all.
No.
No.
So come on in. So the whole building here just makes chill water. And then the cooling towers cool down the chillers while the chillers are making chill water. So here we have 4 different electric chillers that we can start and stop at nighttime. And then we do the same thing over here that we do at the central plant, which is at nighttime we run more electric chillers than we need, and they make more cold water, and we put the water into the chiller, the thermal energy storage tanks. So we fill them with cold water at nighttime, and then in the daytime we turn the electricity consumers off, and then we use the water that we made at nighttime. Cooling tower pumps. Oh, here's some of the media. So water comes in and flows vertically. These are actually supports. They hang on these poles. But yeah, the water flows down through here, through every other one, and air flows through the other ones.
Are they then like hanging off of that somehow?
Yes, these are hangers.
Gotcha.
Big rods for hanging. So these are all the condensing water pumps that take water from the cooling towers, and that water just goes through the chiller to cool the chiller down. The chiller is making chill water, the condensing water is cooling the chiller. And there's always room. They've been adding on to this building for the last 10 years, and they always leave room for growth. So whenever designing a system, you always put in more stuff for growth later on.
So this is just capped off. It's not doing anything just in
No.
case we need it for next time.
The next phase here comes
Yeah.
this way. When they ended last time, these were blank flanges. And then they added 2 more cooling towers, so they're always adding on.
Oh, this is a recent addition here.
Yes, these are cooling towers 5 and 6.
When were these put in? When were towers 5 and 6 put in?
I'm sorry?
When were these recent towers put in?
In the last 2 years.
Oh, okay, yeah, pretty recent. Can you, so when we see this outer shell on here, what's going on the inside? Like if we could do a cutaway of it, what would we see?
Okay, so this is the condenser, and that is the evaporator. The evaporator is insulated. The evaporator is where the chill water is.
Okay.
So up on top you have an electric motor and a compressor. The compressor is pulling on the evaporator, pulling that refrigerant, making it low pressure, and that's what makes the temperature drop. The drop in pressure equals the drop in temperature. So that's where we drop the temperature and make the chill water. And then the compressor pushes out high pressure gas at a higher temperature, and it goes into the condenser. Well, the green is the condensing water flowing from the cooling towers, 73 degrees in and back out, and it condenses that vaporized refrigerant back into a liquid. And then down underneath, the liquid then flows back over through a set of control valves, maintaining levels in both. And then the liquid refrigerant here gets sucked into the bottom of the evaporator where the compressor is pulling on it, and the compressor is pulling that vacuum, so when the refrigerant gets in there, it flashes. And the flashing is what pulls the pressure down.
So if we were to open up the edge of this, would it be one empty tube all the way through, or
There's probably 1,500 tubes, and every year we pull this off. We have a contractor do it. We pull this off, run a brush with water and clean every tube.
Wow.
Because heat transfer is everything. And the fouling of tubes is loss of efficiency. Bad chemistry shortens the life of the equipment, so everything matters. Cleanliness is for heat transfer. Chemistry is to protect the investment of the machine.
And so we're looking at, you said we have how many of these here? We've got 4 of them here?
4 of them here, yeah.
About 1,000 tubes a piece, something like that. And then plus all that many more over at the central utilities plant too. Man, that's a lot.
It's a chiller. It makes cold water.
We're okay over here, right? I'm not.
Absolutely.
I don't want to walk anywhere that'll kill me. I try not to. What is that?
That's the guide vanes.
Huh.
The compressor has a set of blades that rotate. And depending on how much it rotates and how much angle there is on the vanes, depends on how much refrigerant passes. So that's the automatic feature of a chiller.
So there's no way that's on right now, right?
No, this one's off.
Because that is way too quiet to have a compressor running right now.
All chillers have a primary pump. So the primary chill water pump is what pushes a predetermined amount of water through the chiller. And then the outlet from all the chillers goes to what we call a secondary chill water pump. So primary chill water pump pushes water through the chiller, and then the secondary chill water pump pushes water to the customer.
Gotcha.
And usually, just like over at the central plant and here, the pipe going out and the pipe coming back from the customers, we maintain a delta P across there. So those pumps are variable speed. These pumps are across the line.
They're just going.
The pumps that go to the customer, in this case, the East Campus medical side, those pumps speed up and slow down to keep a differential pressure across the supply and the return header.
Is this the same drive that we're seeing over here, the new drive?
Yes. Yeah, that looks...
Same idea?
Yep. Replacement primary. Switch gear. So that's the supply going to the customer, and this is the return coming back. So we monitor the delta P, the pressure between the two.
What is our delta P these days?
This is 68.
Oh, that's definitely going to be a quiz question.
Filters, we're always filtering a portion of it. Above us here is a swirl chamber. A centrifugal type swirl chamber that allows the liquid to be to the outside, and then up top is a red vent, an air vent. So it encourages air to get entrapped up top, and then that's an automatic float, like let the air out. That's the way to get it.
So I'm guessing this is where our electrical engineering friends are doing all of their work.
Quite a lot of switchgear here.
Yeah. And so this is just the 2.8 that's coming from the fuel cell is getting routed around over here, or this is separate?
This is the entire electrical for the Retina Glaucoma Center, the Shiley Eye Center, the
Wow.
John Moore's Cancer Center. All the electricity comes from here. All the electrical systems have two supplies. One, I think it's circuit 113 and 111, but they come in
Yeah.
and everything can be fed from either side. So if there's ever a problem with one side, it
Yeah.
can be powered from the other side. Here's where the generators come in. We have 4 generators over here. We can go look at them.
Sure.
But then
These are backup generators, or they're running all the time?
backup, emergency.
Backup.
So the Shiley Retina Glaucoma Center, all the lighting in all the parking lots, that goes to a chiller. That's a main feed. This is all 12 kV, 12,000 volts. All the diesels are operated from here.
Man, I'm so glad you're the one that comes up and taps on those, because I see touch screens. I'm like, I really want to touch that. But it also says high voltage everywhere.
The diesels
So where does it come in now? It comes in over here somewhere?
Caterpillar. Big cat.
Ah, yeah. So these are our backups.
Yeah, these are backups for the medical side. These are so 1500 kW, 1500 kW, there's 3 megawatts, and then I believe those are 1250s.
These are just straight diesel engines, right?
Yes. We got fuel storage tanks outside underneath. We operate them once a week just to run them, and then the first Tuesday of every month, we actually put load on them. We run them. The state requires, because it's for a medical facility,
Yeah.
it has to have 50% power at least once a month put on them. So we come in early on Tuesday mornings and simulate, and we put loads on them,
Wow.
each one individually, because the load isn't big enough to do all of them.
Yeah. Oh, so they're actually oversized for the 50% tests.
Yes.
Yeah.
Emergency power for medical.
Yeah.
That's the
Boy.
difference between the East Campus chiller plant and the Central plant. At the Central plant, we don't have any patients. There's no medical. There's a lot of research.
Right.
It's really important, but there are no patients on beds.
No life-saving.
Correct. So we fall under a
power.
different set of rules.
Gotcha.
Over here, it's a lot more stringent with the healthcare side.
Is this actually? That's not the actual exhaust of the generator, there, is
that's
it?
a turbo intake.
Oh, okay. I was gonna. There's no
Turbo
way they would
intake.
vent that exhaust inside.
That's the exhaust.
Okay.
Yeah, these are turbos. These are firing these things up is fun. We do it early in the morning, like before the sun comes up, because it usually shoots out a big cloud of black smoke.
Yeah.
And everybody calls and says, "Oh, there's a fire."
There's a fire.
It's not a fire. It's just carbon.
I mean, I guess technically it is a fire, but it's fine. It's inside.
Controlled.
It's in the engine. It's cool.
Exactly.
Cool. Great. So you want to see if we can get into those water towers that we were talking about a
Sure.
moment ago? And that'll kind of wrap us up.
Under the ground is like 30,000 gallons of fuel, diesel fuel. And then they have day tanks up on top. So the day tanks put fuel in the engines.
Where are the day tanks?
These are day tanks.
Oh, these are the ones
So
right
they
here.
have little transfer pumps on them when they go low. So these provide fuel to them. And then these stay full by having a large supply.
Yeah, the tanks underneath us. So these are our towers, same like we saw last time, right? Over at the cogen?
Yes.
Just a little smaller.
Yep. And so water goes in the top. It goes in hot. There's a fan up top that's pulling air in through the louvers. The water is draining down. The air is going past it. And the idea is to break the water up into as many small droplets or expose as much of the water to air as possible so you get the best heat transfer.
So over at the cogen, you said it was about 80% of the reclaimed water was the makeup water, right? Is that
That's
roughly
correct.
what they're running over here?
We're at 60% over here.
Oh, we're at 60%. Okay, I got you.
The basins on these towers, you know, the basins over at the plant are real deep, like they would go up to my head.
Yeah, that's what we would stand in front of.
Are only like 1.5 feet deep.
Oh, that's the basin right there.
That's the whole basin. There's no big, huge volume of water.
Yeah.
It's just a little basin.
Any particular reason for the change, or is it just one person manufactures it one way, or to scale is a different thing?
Side availability of space.
Yeah.
Over here, all the piping is underneath it.
Yeah.
And by just having the water sit in the basin, now you have cold water or cool water able to go do its job, so you really don't need a lot of it.
Right. For anybody in our fluid mechanics class, if we ever ask you what's the pressure drop across various pipe bends and all that kind of stuff, you're seeing why we ask those questions right here. Because there's a lot of them. Oh, we lost Tom.
We're not climbing ladders, are we?
What's that?
We're not climbing ladders, are we?
I mean, I'll climb a ladder. You want to climb a ladder? It's going to get a little shaky here while I climb up this.
This is going to be cool. We're going to open one up and take a peek inside.
Cool. I'm going to hold that for Steve.
We got Steve. Baltimore air coil.
Oh, is that what BAC is? I've always just called it BAC. I didn't know it was...
It's a Baltimore air cool.
Baltimore.
This one's not running. That's no fun. Let's open one that's online. Ah!
Now, how often do you get to see this?
Come on, I'm going. So you can see there's a pulley. It's a belt drive. The motor belts. Oh, it's nice in here. But here's where the water's coming down. You can see in between, you got water and then air. And water's flowing down through them, and air is coming across the side of them. There you go.
And then this is our reservoir at the bottom.
Yep, that's the... and then they all have a little makeup underneath. This is the overflow.
That's pretty cool.
And then you can go into the next one. So you can go through the next one.
That's pretty cool.
Water in.
That's something you don't see every day. That's so cool. Now, the other towers that we had over at Cogen, you couldn't actually go through those while they were operating, right? Because the fill is through the whole thing.
Oh, actually, you could. We can go in underneath the fan.
Oh, you could, yeah. While it's running?
Yeah.
Huh.
I thought you can't stand up.
Oh, well, okay, yeah. Good idea. Good idea. All right, so our last stop is going to be, we are actually going to head inside that parking deck. And just a heads up for everybody that's watching right now, the signal's plenty strong out here, but if we get a little bit shaky inside of the parking deck while we're over there, we'll probably just finish up the stream when that happens. But we're going to, before we get in there, in case we lose our signal, what are we going to be looking at over there, Tom?
Thermal energy storage tanks.
Thermal energy storage tanks.
And
now, these are similar to the giant green tank that we saw over at Central Utilities.
The giant green tank over at the plant is 3.8 million gallons.
Okay.
And here we have 2 million gallon tanks. And I just think it's cool because they're building a parking structure and you go around and around and around in that middle. What do you do with the middle space? It's
Right.
Like, there was some engineer that said, hey, mate, why don't we put a tank in there? Genius.
Genius.
Genius. Let's give them money.
All right, let's head over. Again, for anybody watching, it's going to be a little shaky here as I go down the
I'll grab
ladder,
it.
but we'll, yeah, I think I'll hand you off to Tom for a moment here.
Oh, you got to hold that thing.
Yeah, you got to hold the bottom.
Yeah, that's cool. I've never seen one of these. Now, this is cool stuff. Where's the button?
You want me to take that, Tom?
Yeah.
Or Steve?
There's your guy.
Did it twist around? Little selfie for you.
That's a neat down though.
Cool. You gonna be our cameraman now, Tom?
No.
Okay, I got it.
Real quick, there's chemical barrels down there and chemical injection pumps. I always want to make it impress upon anybody in the engineering field. Chemistry is the key to everything. Proper chemistry, it'll make the equipment last longer, proper maintenance and cleaning, but there is a lot of chemicals going. It's just sulfuric acid, there's
You
at the plant.
want to go check them out? We can take over there if you want.
We can take a quick peek. And all of this stuff is it alarms over at the central plant. This is our chemical feed station. There's a lot going on here. My computer, I control this from the other side, from the power plant. So I can control everything over here. Anything that goes into alarm over here, it's inaudible, and then we send people out here to fix it. So these are all the different chemicals, the sulfuric acids and inhibitors and cooling water treatment, microbiocides.
Now we saw a bunch of these over at, well, actually, I guess it was after the last stream, but the central utilities plant has these too, right? They're just bigger.
Yes, chemistry, you gotta we keep the chemistry at pH at 7.2. We let our conductivity cycle up. City water conductivity is 1,000 micromoles, and we let it cycle up to 4.5 times, so 4,500. And then when it goes above that, you have to dump it and replenish it with fresh water to keep the conductivity down.
Right.
High conductivity causes plating in heat transfer tubes, and scaling and plating is no good because, again, it diminishes heat transfer.
Right. Oh, Tom, I meant to say, if you ever come across these that you don't want anymore, old valves, anything like that,
Absolutely.
send them my way.
You got it.
Because we've got a process lab that they do in their senior year. And one of the things that we like to do is have various sizes of the actual equipment available.
Oh, ball valves, globe valves, gate valves.
Needle valves, whatever you got.
Butterflies.
Because, you know, you turn this here, and we know it's, you know, stopping the flow, but it's another thing to actually see the gate or to see the ball spin or something like that. So
Got
if
it.
you ever got a spare, we'll take it.
We always got spares. PFM.
There it is. There's our fuel cell.
Magic.
So for everybody watching the chat, we're going to have another video a little bit later, maybe in the week, where I go over some of the ideas behind what's inside of that box. So now we're going to head into the parking deck. Again, this, I think we'll be okay. It's a pretty strong signal out here, but just in case we drop it, that will be the end of the stream by the time it drops.
How many people are out there?
I don't know, I can't see it.
Oh, gotcha.
But if they complete their quiz, it'll be about 120 of them, just in our class.
What a neat opportunity. You guys have a great professor.
Oh, so kind of you to say.
And his assistant. Well,
So this parking deck was put up, I want to say it's like 2 years ago now, right?
oh, it's been it's longer than that.
Oh, really? Time flies.
Time flies. So there they are. Tank number 1 or 2, or 1 and 2. We're going to keep from getting run over here. The closer you get to them, the cooler it is.
That is so neat. This is right in the center of a parking deck. That's not that much smaller than the ones over there
No,
at the central utilities.
Look how cool that is.
Wow. All right, now, so the piping that we're seeing here, are these returns or feeds?
They are both.
Or I guess they could be both, right?
They
It
are
depends
both.
on which cycle we're in.
Yep, we got 4 pipes down here below us. And those orange-headed valves, those are all motor-operated valves, electric motor-operated valves.
Now oh, sorry.
I think 2 million. 2 million and 2 million.
Now, are these operated automatically, or do you handle these over
There's a
from
lot of
central
automation
utility?
that happens over here as far as level control.
Yeah.
But as far as giving us the ability, automation is great, but you always have to have the ability for an engineer to intervene
Right.
when things go awry or when.
Now, this structure that I see here, you got a red valve followed by a blue piece followed by a red valve on the other side. That shows up a lot, not just on these kinds of systems. What are we looking at every time we see one of those?
That is a backflow preventer.
Okay.
A backflow preventer. So it's the supply from the city, and whenever you have a city water supply going to any engineering process, you have to have a backflow, just in case the process overpressurizes the city pressure, with the possibility of contaminating the city water supply system with processed water. So every time city water comes into any process, there's always a backflow preventer, and that prevents the backflow of pressure into the city water. That's to protect all of us.
And so those show up, I mean, basically anywhere, right? You can go in front of most of the buildings around campus and
Home
see
Depot, Lowe's,
a structure
Walmart,
that looks
Kmart,
something like that.
every shopping center has them, and they usually have them chained so that you can't, so somebody
Nobody
can't
can-
come
yeah.
over and close them.
So we got 2 million gallons and 2 million gallons in these.
A lot of thermal energy.
Yeah. And so just for anybody who might be here that didn't see our first stream where we described how these things work, roughly what's the flow look like inside of these?
Down at the bottom, there's a very large distribution header that goes around in a big circle on the bottom with holes in it pointing down. And then there's the same type of distribution header on the top, down about 6 feet. And again, it's a PVC pipe, goes the entire circumference inside with holes in it. So when you jump into a swimming pool on a hot day without circulation, the surface is warm, but as you go down towards the bottom, or if you go into a lake, the surface is warm, but as you go down deeper, that's what they call thermocline. It's colder as you go deeper.
Right.
And unless you mix it up, there's a fine line. And we can see a very fine line, and here on top is 58 degrees, and down below is 40.
And when you say you can see that, you're monitoring these over at Cogen, right?
Inside those stainless steel boxes are nothing but temperature sensors every 2 feet.
Wow.
So we can see the thermocline is the term, and that tells us where the 40 stops and where the 50 begins. And as long as you don't mix it up, it's a pretty defined line. It goes up and down, 58 on top and 40 on the bottom.
So do these have baffles inside it to keep it from mixing? It's just an open tank of water all the way down.
It's that header on the bottom that has all the holes in it pointing down, so when water's going in the bottom, it kind of...
This was actually a simulation that some of our students worked on last year. Was a company had a tank like this they were trying to design a thermocline for, and the students needed to know, well, what's on the inside, right? Do we have to model all baffles or anything like that? And they said, nope, it's just a big open tank with low flow rate.
On the bottom and a big distribution head on. If you just don't want to squirt water in there, because that would just...
Yeah, that'll mix everything up, right? Very cool.
The round thing on the side is the entry, the human entry point. So if they were to drain
the bigger one down here.
The insulation, take the insulation off and unbolt the flange, and that's how you get inside.
How often do these get drained and
probably
inspected?
Every 5-10 years.
Oh, okay.
No intention to ever go in there.
Yeah, I mean, there's not much in there that could really break, so.
Nope. To clean out the sediment after a while was
right.
Work. Insulation, a lot of insulation.
Yep.
That's it. That white PVC pipe down there, that 14 inches overflow.
This one. Now, why would there be an overflow at the bottom of a tank?
An overpressurization of one tank, or one tank being isolated.
Uh-huh.
If the automatic valve's closed on the one tank, it's going to push all the water into the other tank.
Oh, okay, yeah. Gotcha.
So instead of having it go out the top, it has an overflow.
Right. That is pretty neat. I had no idea these were sitting right in the middle of a... You know, I got to hand it to whoever actually came up with the color scheme on the outside. They're not unappealing to look at, right? For a giant tank, that's not half bad.
Some engineer.
Right?
Another form of engineering.
That's not half bad. Like, it's...
Make it look nice.
Yeah. Not that you have an ugly system set up over at Central Utilities.
Green is our color.
Yeah. Got a little tree in the middle. I'm actually semi-surprised there's not a little seating area down there, but...
And that's all stormwater.
Which one?
Stormwater runoff.
Inside of these?
All these parking structures, they all drain to an area like this.
Yeah.
So it looks like a lake down there when it's raining.
Wow. Okay, maybe it wouldn't be a good idea for a little seating area. All right, well, for our second stream for the cogeneration facility, I think we're going to wrap it up here. Again, Tom, can't thank you enough for all the time that you're spending with us here. We are always keeping in mind other ways that we can work with you to see more interesting stuff around. Let me come over here. You're all shaded out because of the sunlight behind you. Yeah, thank you so much, Tom. We will definitely check in with you again here whenever we come up to the next one.
Look forward to it.
Cool. Let me go ahead and switch this around. Flip the camera, and I'll just say peace. Hey, there's me. I've actually been here the whole time. So we're going to go ahead and wrap this up for today. If you're in our class, keep an eye out for the quiz, probably later today or tomorrow, something like that. And then we'll keep in touch with you. Stay safe out there, everybody. Have a great day. See ya.